Okay, so now we understood some of the basic concepts. We defined what a system was, what are the different kinds of variables that are used, what's the difference between a state function and a path function. So when we now know these, and then we also understood, we also revised some of the basic ideas of the kinetic theory of gases, the Boyle's law and the Charles law and the Dalton's law, and PV is equal to nRT, and how we came up with the idea of the molar volumes, molar volume and things like that. So now let's move to the very first law, or the zeroth law of thermodynamics. Now there's an interesting story. The zeroth law came after the first law, so it's more basic, but since it came after the first law, we couldn't name it the second law of thermodynamics, but we had to name it something which is more primitive than one. So that's why we came up with the idea of zeroth law. Okay, I'm glad that there was no any fundamental law, then we would have to go to a negative number or something like that, which is crazy, right? So let's discuss the zeroth law of thermodynamics. It is an extremely simple law. You must have already had extremely good explanations and extremely good ideas about this previously. I'll just draw a diagram and try and just explain the simple concept that is in the zeroth law using this diagram. Okay, so let's assume that you have a system in which there are three separate bodies, namely A, B, and C. Now A and B are separated by an insulator, a thermal insulator, and there can be no heat exchange between the body A and the body B. So we will assume that they are at different temperatures. One is at a hotter temperature and the other is at a colder temperature. So when we have an insulator, there is no heat being exchanged between those two, right? Now, A and C are they are in contact, and there is a possibility of heat exchange between these two. And also C can exchange heat with B. That means after some time, A and C will be in thermal equilibrium with each other. What do you mean by thermal equilibrium? The temperature of both these bodies will be same. And the same thing will happen with B and C. Body B and C will also be in thermal equilibrium with each other. So by this, we came to the understanding that, okay, if A and C are in thermal equilibrium and B and C are in thermal equilibrium, then A and B have to be in thermal equilibrium with each other. That is as simple as like the zeroth law, right? It's extremely simple concept. So this is the concept that you basically use to measure your body temperatures, right? So you would like to know what is your body temperature. So there is no direct way of measuring your body temperature, but by the use of a thermometer. Now you have the direct ways of measuring thermometers with the body scanners, with the IR scanners. But previously, when you used to have thermometers, this was the law that was being used. Like the zeroth law of thermodynamics was actually helping you to find out the body of your temperature. Why? Because when you get your thermometer and bring it to thermal equilibrium with your body, and that's why you have to wait for a certain amount of time so that the temperature of your body is equal to the temperature of the thermometer. And then you measure, then you read off the temperature of the mercury that was in the thermometer. And that would have given you the temperature of your body. Right? So this is basically the zeroth law of thermodynamics. Nothing very astounding here, but extremely basic, and we should try and understand this. Okay. Now, let's move to the first law of thermodynamics, which is much more interesting and much more fun. Okay. So, first law. This law deals with energy conservation. We have studied energy conservation when we were in school, right? So we always knew that energy cannot be created nor it can be destroyed. It can only be transformed from one body to another. So basically, that is the idea of energy conservation. And in here, we just mathematically write that idea down. Okay? So let's assume we have a system in which you have a cylinder with a piston, okay, and you have gas inside the piston, inside the cylinder, okay. So you have a piston in here, okay. Now, you are giving heat to this body. Okay, so you are providing heat to this body. The piston has the ability to move, okay? So the piston can move. Now, the heat that you have provided can be used to move this piston in such a way that the volume of this whole thing expands. So your heat that you have given can be used to increase the internal energy, so to increase the volume. So your heat goes to these molecules, and these molecules start to vibrate fast, and when they try to vibrate fast, they try and push the piston far off, like to expand. So your heat can go, so you give the body some heat, and that heat could be used to do some work. So if you expand the gas, you're doing some work. So that can be used to do some work. The remaining goes into the molecule's internal energy. So let's assume that you have $100 to spend, and so I gave you $100. Now what you can do is you can use this $100 to either buy something, right, or save that in your bank, right? You save that in your account. So it's like that. I gave you $100, you can buy something, and whatever remains goes to your bank. This is basically the first law of thermodynamics. Now, extremely simple law, right? So any change in energy that you get, basically this is internal energy, is the amount of heat that you gave to the body minus the work done, because there was some energy that was lost in doing some work. In here, I would like to define work, because it is extremely important, because it is the sign convention that confuses people most of the time. So now, if I have to define work, as we have studied in physics, is basically force times the displacement, right? So this was work, right? Work is a scalar quantity. It's a product of two vector quantities. It's a dot product, so the dot product gives a scalar quantity. Okay, so this was work. Now, we know that pressure is force by area, okay? Now, force then becomes pressure times the area, right? Okay, force then becomes pressure times the area. So in here, what you can write, in place of the force, you can write the pressure that was being being applied into times the area times the dx. So in here, the area will be the cross-sectional area of the piston itself. The pressure will be the pressure that is being applied by the gas molecules on the piston, and dx is the amount of displacement that this piston does. Okay, so this becomes P. This then we can write down as dV. So work in here becomes P times delta V. Now let's assume, so there can be two things that can happen. Now, when you are expanding the gas, so let's assume that the gas was expanding, okay? It can be a case that the gas is expanding. When will you say that the gas is expanding? When dx is a positive quantity, only then you will say that the gas has expanded. So the dx is a positive quantity. You increased so you increase this distance, you expanded, right? So when the dx is a positive number, then the force is applied, the force was being applied in this direction, in the upward direction, and the displacement happened in the same direction. So force and displacement were in the same direction. Therefore, during expansion, I will assume that positive work has been done. Okay? My assumption. And this assumption is the one that mostly the physicists used to follow. I find this this convention really easy to remember, really easy to understand, and that's why I use this. Some people can use a different convention. Okay, they can, but in that case, you'll have to change the signs in here. Okay, now the expanding, I said during expansion the dx is a positive number and therefore work is positive. During compression, the opposite thing happens, and dx becomes a negative number and therefore work becomes a negative value. So during compression, we say negative work is done. During expansion, we say positive work is done. During expansion, we say that the system, which is inside, is doing work on the surrounding. During compression, we say that the surrounding is doing work on the system, right? So you're compressing it. So the outside is doing work on the system. Compression, negative work, okay? So in here, let's like simplify this, or let's talk about like small quantities of heat that was given, of work that was performed, and the change in internal energy. So we formalize that using an equation which looks something like this. A small change in internal energy is basically a small change, the heat that was given minus the work done, the small change in that work. Now, I have used a different symbol for a small change in internal energy, which is D, like, but in here I'm using a Greek small delta, right? So small delta in here. Why? Because work and heat, these two are path functions that we studied earlier, right? So work and heat are both path functions, and we know this. So if you're not convinced about this and want to learn more, so there are other videos in which I have dealt with this in more detail. And D is a state function, and therefore a perfect differential, and that is why I'm like writing it in here as dE and not del Q and del W. Okay, so this is the general idea of the first law of thermodynamics. In here, please keep in mind that during expansion we have assumed that the work done is being positive, and then this law is being followed, right? So you got some Q, you invested that, and the rest is in your internal energy. Really easy to understand this. And if someone, like generally the chemists, they do is they flip this convention. They say that, okay, during expansion, since I am like losing some kind of like energy, and this is how they like look at it, they say that during expansion I will assume that work done is negative. So okay, you can do that, but you'll have to change the sign in here. That's it. Okay, Q, there is also a sign convention with the Q. So when Q is a positive quantity, then that means heat is getting in. So Q is positive. I'm giving Q positive. So this is an endothermic process, right? Endo means in. This means in. So heat is getting in. And when is negative, we call it an exothermic process. Why? Because heat is getting out. Okay? This convention is basically same for both physicists and chemists, but there is a small change in convention when people define these in two different ways. I find this easier because if we do that, this makes more intuitively makes more sense. Okay, so this is the first law of thermodynamics.